If you have ever tried to solve a system of 3 linear equations by hand using substitution or elimination, you know what this looks like. There is a cleaner way. By translating these problems into the language of matrices, we can structure the math so a computer does all the heavy calculating for us. Look at this starting problem. We have 3 equations, and we've carefully aligned the variables so the x's, y's, and z's form perfectly straight vertical columns. To let a machine solve this for us, our first step is to strip away the human algebra and build a machine-readable structure. Watch how we pull the numerical coefficients away from the letters. We are extracting these numbers to build the skeleton of our main 3x3 matrix, which we'll call matrix A. But notice the gap in the second row. We have 2y plus 5z, which means the x variable is completely missing. To maintain our strict grid alignment, we must explicitly place a 0 in that empty column. Now, matrix A is complete. To prove this separated format works, look at how matrix multiplication functions. Taking the dot product of the top row and our variable column perfectly recreates our first equation. 1x plus 1y plus 1z equals 6. Try applying that same dot product logic to the third row yourself. Multiplying the elements of the third row by the variables gives us 2x plus 5y minus 1z equals 27. Successfully extracting these coefficients gives us a clean mathematical setup. Matrix A times matrix X equals matrix B. Our goal now is to isolate matrix X, the variables we actually want to solve for. That means we need to move matrix A off the left side of the equation. In standard algebra, you would just divide by A. However, in matrix algebra, division does not exist. Instead of dividing, we use an inverse matrix. This a to the power of -1 is the specific mathematical tool required to cancel out matrix A. Methodical emphasis. Here is the most rigid rule in matrix math. Multiplication order matters. Because we multiply by the inverse on the far left side of our X matrix, we must also place it on the far left of our B matrix. On the left side, the inverse and the original matrix neutralize each other. They vanish entirely, leaving exactly what we want. X equals the inverse of A multiplied by B. By following the spatial rules of multiplication, we have structured a final equation that is ready for computation. Now that we have isolated X conceptually, the actual number crunching to find that inverse matrix gets handed off to a calculator or computer program. There is one mechanical caveat to watch for. If your calculator tells you the determinant of matrix A is exactly 0, the inverse cannot be calculated. That means your system of equations either has no unique solution at all or an infinite number of them. Assuming the inverse exists, the calculator multiplies our new 3x3 inverse matrix against the vertical column of our constant numbers, matrix B. The output gives us a single column locking in our answers. X is 5, y is 3, and z is -2. To run this process on any linear system, follow these 3 strict steps. Extract your coefficients and fill any gaps with zeros. Set up your ax equals b equation, and multiply by the inverse matrix on the left to find your solution.